When people talk about machine learning and security, they often speak as if there is one general approach, but there are multiple learning styles, and each one fits different problems. For Security AI Plus, you want to be able to recognize which learning style matches a scenario and what risks and trade-offs come with it. The three big categories you will hear are supervised learning, unsupervised learning, and reinforcement learning. These names describe how the system learns, meaning what kind of feedback it gets while it is learning. If you understand that feedback relationship, you can predict what the model is good at, what it struggles with, and how it can fail in ways that matter for security. That matters because exam questions often describe a use case, like detecting anomalies, classifying malicious activity, or optimizing a decision process, and then ask you which approach is most appropriate. When you can connect the scenario to the right learning type, the answer choices stop looking like random jargon. You start making choices based on what the model is being taught to do. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at Cyber.Author.me in the Bare Metal Study Guide series. Supervised learning is the most familiar category because it looks a lot like studying with an answer key. In supervised learning, the model is trained on labeled examples, meaning each training input comes with the correct output label or value. For security, you can picture a dataset of past events labeled as malicious or benign, or phishing or not phishing, or normal login or suspicious login. The model learns patterns that associate input features with the labels, and then it uses those patterns to predict labels for new inputs. The strength of supervised learning is that it can be very effective when you have high-quality labeled data that represents the real world you care about. The weakness is that labels are expensive and imperfect, especially in security, where ground truth is hard to establish and attackers change behavior over time. Supervised learning can also inherit biases from the labels, meaning if your past investigations missed certain threats, the model may learn that those threats are rare or irrelevant. In exam terms, supervised learning fits scenarios where the goal is classification or prediction with known categories, and where you can reasonably define what right looks like. One of the most important supervised learning trade-offs in security is the dependency on label quality. If your labels are wrong, inconsistent, or outdated, the model will learn the wrong thing, sometimes very confidently. In a security context, labels might be wrong because an incident was misclassified, because the investigation ended early, or because an attacker successfully disguised activity. That makes supervised learning vulnerable to learning false associations and missing real threats. Another trade-off is that supervised learning is often better at recognizing patterns it has already seen than at spotting truly novel attacks. It can generalize to similar variations, but if a threat looks very different from the training set, performance can drop. This is why defenders often combine supervised models with other approaches, like rules, heuristics, or anomaly detection, to cover more ground. If the exam describes a system that learns from known attack examples and aims to label new events as malicious or benign, supervised learning is a strong match, but you should also be ready to recognize the risks of reliance on historic labels. Unsupervised learning is different because it learns without labeled answers. Instead of learning with an answer key, the model looks for structure in the data on its own, like clusters, patterns, or unusual points that don't fit. In security, this is often used for anomaly detection, where the goal is to identify activity that is unusual compared to a baseline. For example, an unsupervised system might notice that a certain user's login pattern suddenly changes, or that network traffic shows an unfamiliar pattern. The strength of unsupervised learning is that it can highlight unknown or emerging behaviors, which is valuable in a threat landscape where novelty matters. The weakness is that unusual does not always mean malicious, and security environments are full of legitimate changes that look odd, like software updates, new employees, or seasonal workload shifts. That means unsupervised systems can create many false positives if they are not tuned, monitored, and placed in a workflow that expects investigation and triage. For exam scenarios, unsupervised learning fits when the problem is to explore data, find groupings, or detect anomalies without reliable labels. A key unsupervised learning concept for security is that it depends heavily on what normal looks like, and normal is not stable. If your environment changes, what was once unusual can become normal, and what was once normal can become unusual. This creates a drift challenge, where the model's notion of baseline needs updating. If it updates too quickly, it might absorb malicious behavior as normal, which is dangerous. If it updates too slowly, it might keep flagging legitimate new behavior as suspicious, which is noisy. Another challenge is interpretability, because unsupervised outputs can be hard to explain, like saying an event is an outlier without a clear reason. That can frustrate analysts and reduce trust, which increases the chance the alerts will be ignored. In exam terms, when you see scenarios emphasizing unknown threats, lack of labeled incidents, or the need to detect deviations from baseline, unsupervised learning is often the most appropriate category, but the best answers will also recognize the need for monitoring and human validation. Reinforcement learning is the third category, and it is the one most likely to feel unfamiliar to beginners because it is about learning through interaction and feedback over time. In reinforcement learning, an agent takes actions in an environment and receives rewards or penalties based on the outcomes. The agent's goal is to learn a strategy, called a policy, that maximizes reward. This learning style is often used in domains where decisions are sequential and the best action depends on what happened before. In security, reinforcement learning can be applied to things like automated response strategies, resource allocation, or adaptive defense, where the system must choose actions and learn which ones lead to better outcomes. The strength is that reinforcement learning can learn complex strategies that are hard to handcode. The weaknesses are that defining a safe reward function is tricky. The system can exploit loopholes in the reward, and exploration can cause risky behavior if not constrained. For exam scenarios, reinforcement learning is a fit when the problem is about optimizing decisions over time rather than classifying a single event. A particularly important security concern with reinforcement learning is that the agent might learn a strategy that maximizes the reward in unintended ways. If the reward is poorly designed, the agent can learn to game it, producing outcomes that look good in the metric but are bad in reality. This is sometimes called reward hacking, and it is a serious risk in any automated system that has power to affect the environment. Another concern is safe exploration, because reinforcement learning often requires trying different actions to learn what works, and in security, trying risky actions can be unacceptable. In practice, reinforcement learning for security often needs strong constraints, simulation environments, or human oversight to prevent harmful actions. For exam purposes, you don't need to build an agent. You need to recognize that reinforcement learning is about action and feedback loops, and that safety boundaries are critical. If a scenario describes a system that learns how to respond over time based on outcomes, reinforcement learning is likely in play. Now let's compare the three directly through the lens of what kind of question you are trying to answer. Supervised learning answers questions like, given this input, which label should I assign based on examples with known labels? Unsupervised learning answers questions like, what patterns exist in this data, and which points are unusual compared to the rest? Reinforcement learning answers questions like, which action should I take next to achieve the best long-term outcome? That framing helps you map exam scenarios quickly. If the scenario emphasizes labeled attack history and classification, supervised is the natural match. If it emphasizes unknown threats and deviations from baseline, unsupervised is the natural match. If it emphasizes sequential decision-making and optimizing responses, reinforcement is the natural match. The exam will often present answer choices that include all three, and your job is to match the learning style to the nature of the feedback and the goal. It's also important to compare what each learning style needs in terms of data and governance. Supervised learning needs labeled data sets, which means you need processes for labeling, validation, and handling label errors. Unsupervised learning needs good, representative data streams and baseline management, which means you need monitoring for drift and policies for updating baselines safely. Reinforcement learning needs an environment where actions and outcomes can be measured, and a reward structure that aligns with security goals, which requires careful governance and safety constraints. All three need access control, because training data and model outputs can be sensitive. All three need monitoring, because performance changes over time. But the kind of monitoring differs. Supervised models are monitored for classification performance changes. Unsupervised models are monitored for alert volume and baseline stability, and reinforcement learning agents are monitored for action safety and unintended strategies. In exam terms, the best answers often reflect not only which learning style fits, but also what controls should surround it. Another comparison that matters is how each approach handles novelty. Unsupervised learning is often better at surfacing novel patterns because it is not constrained by predefined labels, but it pays for that with higher false alarms. Supervised learning can be very strong on known categories, but can struggle with truly new attack types that don't resemble the training data. Reinforcement learning can adapt strategies over time, but only if the reward structure pushes it toward the right behaviors and the environment provides meaningful feedback. Attackers can exploit novelty by intentionally changing behavior, which is why relying on a single learning style can be risky. Many real systems combine approaches, like supervised classification for known threats and unsupervised anomaly detection to catch unknown ones. The exam may not ask you to design a full system, but it may test whether you recognize that trade-offs exist and that layered approaches can reduce risk. Recognizing trade-offs is a core security skill. A beginner misconception is that unsupervised learning is always better because it finds unknown threats, but it can drown a team in noise if not managed well. Another misconception is that supervised learning is always reliable because it has labels, but labels can be wrong and the world changes. A third misconception is that reinforcement learning is always too advanced for security, when it can be useful in controlled settings, but only with strong safety boundaries. The mature security stance is to ask what problem you are solving and what constraints you have, then choose the learning style that fits, and then wrap it in controls that reduce the predictable risks. On an exam, this often means the best answer is the one that matches the learning style to the task, while also respecting constraints like data quality, operational impact, and the need for human oversight. If you keep that mindset, you can handle tricky scenario wording without being pulled into the wrong choice. The practical skill you want to carry forward is being able to look at a security use case and immediately ask, what feedback does the model get while learning, and what is it trying to optimize? If the feedback is labeled examples, you're in supervised territory, and you should think about label quality and generalization. If the feedback is structure in unlabeled data, you're in unsupervised territory, and you should think about baselines, drift, and false positives. If the feedback is reward and penalty based on actions, you're in reinforcement territory, and you should think about safe exploration and reward alignment. That is the comparison in one breath, and it's a useful breath to practice saying out loud. When you can say it clearly, you can apply it quickly. That's exactly what exam scenarios demand, and it's exactly what defenders need when deciding how to use AI safely in real security workflows.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.